for our 5.3 unit, which is about factoring polynomials and then using that factored version of a polynomial to sketch it out. So the first question here just asks us, lists a series of binomials and asks us which is a factor of this polynomial. And so this is a factor theorem question. Factor theorem. So the factor theorem states that a binomial is a factor of a polynomial if its root, when punched in for each of these x values, gives us 0, outputs 0 from that function. So I'm going to call this polynomial p of x, this polynomial expression. So let's say let p of x equal plus 6. Okay, so for question A, if we have this binomial x plus 1, that is a factor if the root of this factor, when punched in, gives us 0. So when we take that root and put it in as an input of this function, and it spits out 0, well, then it's a factor. So let's just try it. So p of negative 1 gives us a negative 1 cubed minus 6 times negative 1 squared plus 5 times negative 1 plus 6. And we can punch that into our calculator, but we can also know that negative times a negative times a negative is a negative, but a negative squared, that becomes positive. So we overall get negative 6 times positive 1. 5 times negative 1 is negative 5 plus 6. And I want to remind you guys, we're not actually concerned with how much this is equal to. We just care if it's equal to 0 or not. And I can see I have 3 negative terms and then a positive 6. So we don't have enough positivity to counteract all this negativity. This is not equal to 0. So therefore I can conclude that x plus 1 is not a factor of, I'll call it p of x. I called it p of x, right? Okay. So moving on, we'll try question B, which is x minus 1. So x minus 1, that will be a factor if p of 1 gives us 0. So I'll punch in 1 for x, I'll cube 1, and I'll take away 6 times 1 squared, plus 5 times 1 plus 6. And we get 1, take away 6, plus 5, plus 6. And this is very similar experience to the first question, where everything was negative except for one positive term. Everything's positive here except for one negative term. And that negative term is not big enough to counteract all that positivity. So that's not equal to 0 either. Therefore, x minus 1 is not a factor of p of x. Oh, oops. All right, I'm going to zoom in a little bit and focus that. All right, let's keep going. So then we have the factor, potential factor, x plus 2. So we're checking really what p of negative 2 will be when we punch negative 2 in. So we get negative 2 cubed minus 6 times negative 2 squared plus 5 times negative 2 plus 6. And negative 2 cubed is negative 8 minus 6 times 4 minus 10, take away 6. And, oh, no, add 6. And so, again, I don't really need to add these together. I can see I've got negative 8 and negative 24, take away 10. The only positivity is a 6 here, so that's not equal to 0 either. So therefore, x plus 2 is not a factor of p of x. So lastly, we'll try D. So we'll take x minus 2. And so then we're looking for what p of 2 is. Okay, well that'll be 8 minus 6 times 4, which is 24, plus 5 times 2, which is 10, plus 6. And now we have 3 positive terms and 1 negative, but this one's a big negative term, much bigger than each of these individual positive terms. I think we're actually going to get to 0 when we do this. So I'm just going to double check. 8 plus 10 is 18, plus 6 is 24. Take away 24 is 0. So therefore, x minus 2 is a factor of p of x. And that's the only one. Okay. So, moving on to question 2. Question 2 asks us to sketch this function, which you may notice is the same expression is this one, so we already know a factor of this expression. So we're going to exploit the fact that we know that x minus 2 is a factor of this. Okay. So the first thing we're going to do is we're going to utilize the fact that we found in 1D that x minus 2 is a factor of what they call now in question B f of x. So therefore, f of x, which is equal to x cubed minus 6x squared plus 5x plus 6 is also equal to x minus 2 times some expression. I'm just going to grab a couple other colored pens. And so, to find out what this other component of this expression is, we're going to divide this guy by that factor to determine the leftover part of that expression. So to do that, we use long division of polynomials. So we set up a long division, or as Cambalodus calls it, tall division. That's 5x plus 6. And we've already done all our practice with long division, so this is pretty familiar at this stage, so I'm going to go through it pretty quick. Divide, I'm going to multiply, I'm going to subtract. Negative 6 take away negative 2 is like negative 6 plus 2, which is negative 4x squared. I bring down 5x. I divide again, so x into negative 4x squared is negative 4x. I multiply that through, and I get negative 4x squared plus 8x. And then I subtract them. So that gives us negative 3x plus 6. And I say, okay, x into negative 3x, that gives me negative 3. Multiply negative 3 by both of these guys, I get negative 3x plus 6. And when I subtract them, I'm going off screen there, I end up with 0. Okay, so that tells me that this quotient is really this value. So, in other words, f of x is equal to x minus 2 times x squared minus 4x minus 3. Okay, and that is a quadratic equation, a quadratic expression, so I could factor that, or I could use the quadratic formula. Okay, interesting. That's gross. So is there any numbers that add to negative 4 but multiply to negative 3? I feel like maybe there isn't. Negative 4 plus 1. No, negative. I don't think so. So I'm going to use a quadratic formula here. So I'm just going to say x is negative 4 plus or minus square root negative 4 squared minus 4 times 1 times negative 3. And that's all over 2. So in other words, we're going to have two roots, one at 4 plus or minus at 16 plus 12 over 2. Where x is 4 plus or minus root 28 all over 2, which is equal to 4 plus or minus 2 root 7 over 2. And I can divide each of these guys by 2. So I also get solutions that x is equal to 2 plus or minus root 7. Okay, so I'm going to move on to the second page here. All right, so we know that this is 2 continued. That's not how you spell continued, I don't think. I think it's like, there we go. Okay, fine, whatever. So we know our f of x is equal to x minus 2 times x squared minus 4x minus 3. And if I'm looking to express the roots of this expression, okay, I get a root at x equals 2, and I get roots at x equals 2 plus or minus root 7. Now I'm going to need a calculator for that because I don't know how big 2 plus root 7 is. So, in other words, 2 plus root, where's the root on this thing? Root 7. That's okay, so x is equal to approximately 4.6, and x equals approximately 2 minus root 7, which is negative 0.6. Okay, so now I can sketch those as x-intercepts. So I'll go ahead and sketch this guy out. So I know I've got an x-intercept at 2, an x-intercept at 4.6, and I got an x-intercept at negative 0.6. Okay, and that gets me started. Next, that's my x-intercepts. Okay. So next I want to find out my number of turns. So I just check and I say, okay, this is a third degree polynomial. This is a third degree polynomial. So therefore, there's going to be 2 turns, or curves. I also know the leading coefficient, the number in front of the x cubed term, is a 1. So the leading coefficient is positive 1. So that means this thing is going to finish up going to positive infinity. So I'm going to draw a little positive arrow going up there. Okay. And next I'm going to find my y-intercept. So my y-intercept is when x is 0. So f of 0, well, it's easier. I could plug 0 into each of these guys. I get 0 here, 0 here, and 0 here, and end up with negative 2 times negative 3. However, it is always easier to look at our original expression. And this turns to 0, this turns to 0, this turns to 0. We end up with just a simple 6. So f of 0 is 6. That means 1, 2, 3, 4, 5, 6. These do not have to be to scale. These are sketches, not diagrams. Okay, and so we have no multiplicity. So multiplicity, there is none. So that means there's no kisses and there's no inflection points. And so now we're going to just connect the dots. So this one looks pretty straightforward as is. So I'm going to connect the dots like so. Going to come down and head up to positive infinity. And so we look something like that when we're done. Okay. I could always do a table of values and test an extra point if I want, just to make sure when I plug in f of 3 I get down here. But I'm pretty confident that's my graph. So we'll move on to question 3. Okay, so question 3 asks us to determine all the possible rational roots of the polynomials using the rational roots theorem. All right. So for question 3a, I know my leading coefficient is a 1. So those will represent my denominators there. So my possible denominators are either positive or negative 1. My possible numerators are the factors of 6, which are plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. And so the potential roots are, so the possible roots are any of these numbers divided by either of these numbers. So in this case you have 1 over 1, or negative 1 over 1, or 1 over negative 1, or negative 1 over negative 1. Either way you get plus or minus 1. And actually, it's the same thing with 2. When you put any of 2's over either of these, you end up with only a possibility as a plus or minus 2. And the same with plus or minus 3 and plus or minus 6. So there's our final answer for that one. So next, we'll move to, we have this x cubed plus 3x squared plus minus 4x. Take away 12. And so in this case, again, we have a 1. So our possible denominators are really just plus or minus 1, which is going to make our lives a lot easier. And the possible factors of negative 12 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus, 12. And very similar to the first example, because the denominators are really only positive or negative 1, they don't fundamentally change the options here, and really our answers just become the numerators. So the possible roots are just plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And those are really the only possible rational roots. Of course, there could be irrational roots. All right, so if we look here at this next example, 3x cubed minus 3x squared minus 15x plus 6. We say, oh, okay, well, the factors of 3 could be plus or minus 1 or plus or minus 3, right? And for our numerators here, we're looking at the factors of this last term, which are plus or minus 1. They're the same ones as above here. Plus or minus 2, plus or minus 3, or plus or minus 6. Okay, so that means our possible roots are any of these numbers over plus or minus 1, or any of these numbers over plus or minus 3. So let's start with all of these numbers divided by plus or minus 1. So the only options there are plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. Now here's where things get interesting. When I divide by 3, when I put this number over 3, I actually get plus or minus 1/3 of our possible roots as well, or plus or minus 2/3, or plus or minus 3/3, but 3/3 is the same thing as 1, so we actually already have that value written down. Also plus or minus 6/3, but 6/3 is 2, so we already have that expressed here. So these are the only novel roots we get by having a coefficient of 3 in the numerator, or in the first term, the leading coefficient. Okay, maybe we'll do d over here. So d is x power 4 plus 8x cubed plus 17x squared minus 2x minus 24. And this is a similar scenario where our leading coefficient is just 1, so that's a denominator, and our numerator is 24, which actually has quite a few factors, so we're just going to list them out: plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. All right, so that means our possible roots are really just these guys divided by positive or negative 1, which is just themselves. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24, and we are done. Now, you may notice as you move on to question 4, you see these same questions showing up down here. So hopefully those will become a little useful for us. So first of all, we found our possible rational roots for this first expression, which is actually this one here, the first one we did. And when we looked at all the possible rational roots, we only had one rational root for that function when we factored it. It was 2. The others were irrational. But 2 was one of the possible roots that was listed here. Okay, and so then we see this character showing up down here. That's b of x. This one corresponds to d of x. And this one here corresponds to g of x. So we're going to utilize the fact that we've done some of our work already when we get to those questions. Okay. So question 4 asks us to sketch the functions. Now, in order to sketch these functions, we're going to need to factor them. And depending on our polynomial, it may be easy or hard to factor our expressions. Now, I actually think question a of x function is actually kind of easy to factor. So you could find all the rational roots, use the polynomial theorem to find a rational root, use a factor theorem, and then do long division. You can do all that, but there is an easier way to factor. First, I can see common factors. I'm going to factor those out to the front. So a of x is, I'm going to say, okay, I can see x squared multiplies at each of these. I'm going to take out my leading coefficient of -1. And let me just see what happens when I do this. And I open it back up. I want to just make sure this thing isn't frozen. And maybe it is. Oh, okay. It's not frozen. Okay. So I'm going to factor out a negative x squared. I can say negative x squared multiplies into all 3 of those terms. And that leaves me with an x squared here, and a negative x, and a -2. Okay, and this I could then sketch because I can write this as a trinomial factoring, right? So it's common factoring. And now we're going to do trinomial factoring. We're looking for 2 numbers that add to the invisible -1 here and multiply to -2. Are there numbers that add to -1 multiplied -2? I think it's in -2 and 1. Am I right? -2 and 1. I think that is correct. Okay, cool. So that means I could really write that as x minus 2, x minus 1, because my leading coefficient here was just a 1, which allows me just to jump straight to there. And that's, of course, trinomial factoring. Okay. So now that we have a factored function, we can sketch it. So I'm going to start by finding my x-intercepts. They're going to be at x equals 0, x equals 2, and x equals 1. So I'm going to go ahead and sketch those right now. Oh, and it looks like I've got multiplicity here. So I've got some multiplicity. I'm just going to make a note of that because I can see that right there, multiplicity. And that means there will be a kiss because there are 2 roots. It is being squared. It's x and another x. I'm just abbreviating it as x squared. Okay, so that means I've got a root here at 0. I've got a root here at 1. And I've got a root here at 2. Okay, it's going to be kind of bunched up, it looks like. All right. My leading coefficient is, oh no, sorry, this is a 4th degree polynomial. It's power of 4 here. So it's a 4th degree. So there will be 3 turns or curves. And a leading coefficient is -1. So that means it's actually going to be going downward when it finishes. So at the end of the day, we're going to have a downward arrow down like that because it is negative. All right, our y-intercept, well, our y-intercept we've already graphed, is 0. A of 0 equals 0. Okay, there is a kiss. So the multiplicity states there is a kiss at x equals 0. But maybe we're not quite sure if that kiss goes up like this or if it goes down like this. So I'm just going to do a little, maybe it's down like that, or maybe it's up like this. We're not quite sure at this stage, and we don't have to. B, we just want to acknowledge there is a kiss. And F, we're going to connect the dots. So because I'm not sure about whether I'm going to start down here or I'm going to start up here, I'm going to try and connect the dots from the right. So I know it has to go through 2. and it has to come down and hit 1, and then it must have to bounce up, and there we go. There's our kiss, down like that. And there we go. That's a of x, like so. So it turned out we didn't have to do a lot of polynomial factoring. If you can think of any way to avoid it, it's good to do so because it can take a long time, and long division is kind of error prone, I think you'll agree. All right, so we'll move on to 4b. All right, 4b. 4b. All right, so we've got b of x is equal to x cubed plus 3x squared. Take away 4x, take away 12. Now, I did list all the possible roots of this thing. However, I can see this is a cubic graph. I'm going to see if I can get away with factoring by grouping, because I can see that there's a common factor here and a common factor here. I'm not sure how this is going to work out, but I'm going to give it a try. So I'm going to take out a common factor here of x squared, and I'm going to bring out a -4 from these guys. And I'm left with an x and a +3, and -4 times x gives me -4x, and -4 times, 3. There you go. Hey, look at that. That's looking good. So that means we can factor that out to the front. And so we get x plus 3 out in front. And we're left with these x squared and that -4. Okay, so that's our b of x expression. So that saved some time. And we're not quite done until we finished factoring, and I can factor that. So we just used factoring by grouping. And now we're going to use difference of squares. We have a difference, a subtraction between two perfect squares. So I'm going to rewrite this as x plus 3 times x minus 2 and x plus 2. And that is difference of squares factoring. So for 2 questions in a row, we got away with murder, kind of. We got away without having to do all of those factoring steps. So that's nice. Okay, so now we can move on to sketching, because we have a nice factored form. So our x-intercepts are at x is -3, x is 2, and x is -2. I'm going to go ahead and sketch those. So I've got an x is -2 there, and I've got a x is 2 root there, and a -3, so I've got another one out here, so -3. All right. Doesn't look like I have any multiplicity, doesn't look like I have any roots repeated. So this is a 3rd degree polynomial. It's a power of 3 here. So we should be expecting 2 turns. And the leading coefficient is +1, so that means it's going to be ending, moving upward. So it's going to look something like that. My y-intercept, my b of 0. In other words, I could punch in 0 for each of these x's, but those terms would all disappear. I just end up with -12. Alternatively, I could put in 0 here, 0 here, and 0 here, and multiply all 3 of those expressions together. Again, you get 3 times 2, which is 6, times -2, which is -12. So we get a y-intercept down here. Doesn't need to be to scale necessarily, -12. Now, this is already starting to come together for me. I can sort of see how it all fits. Just as a reminder, there is no multiplicity. Oops. So that means we're going to connect our dots and really just come down like this. It could come down a little lower, we're not sure. It doesn't have to change direction when it hits a point. And comes down like so. And again, we got away without doing any gross polynomial factoring. And there's our 4b. Okay. So let's move on to 4c. So in the last example, we saw how easy it was to factor this whole expression if we could just figure out how to do some factoring by grouping. I can see there's common factors here. 3x, and it's going to leave me with an x. Oh, no, 3x squared, I guess. An x and a take away 4. And I can take out a negative 1 here, and I get an x take away 4. Well, look at that. Again, I end up being able to use factoring by grouping to make my life easier. So that's factoring by grouping. And, oops. All right, and now we have a difference. They're not a perfect squares, though. I could factor this by difference of squares if I wanted to, or I could just set this equal to 0 and solve for the intercepts. I think I'm going to do that. I think I'm going to factor it. So that would give me root 3x plus 1 and root 3x minus 1. And that's difference of squares factoring. Okay, so of course that's our c of x, c of x. All right, so now we can sketch. So part 1, we're going to find our x-intercepts. And so we get 1's at 4, negative 1 over root 3, and 1 over root 3. I don't know exactly how big those are, so I'm going to get my calculator out and just help me approximate that. 1 divided by root 3 is 0.5, so I'm going to say 0.6. So it's approximately equal to negative 0.6 and approximately equal to positive 0.6. So those are our 3 roots. Okay, so I'll sketch out 4 first. 1, 2, 3, 4. That's my root at 4. I'm going to have a positive 0.6. So it's 1 over root 3. And there's my negative 1. Negative 1 over root 3, like so. Okay, cool. Next, I'll ask the degree. This is a third degree polynomial. So therefore, there will be 2 terms. Leading coefficient is positive 3. So because it's positive, it's going to be ending, heading upward. So that means it's going to end moving upward like so. My y-intercept, c of 0. Well, I'm going to punch in 0 for each of those, and they're going to disappear, leaving us with a 4. So that means I've got a 1, 2, 3, 4. I've got a y-intercept up here at 4. Okay. So I should be able to connect the dots at this stage. I'll just double check, and of course I do not have any roots that are repeated. So there's no multiplicity. All right, so we'll just sketch this graph then. Looks like it comes down from up here, hits 4, comes down again. Not sure how far down. And if we don't worry about those details, we can always, if we want more detail, you can always get it. You can always punch in another value and find out what output it gets. But that is our graph, c of x, happy graph. Okay. I think I'm going to have time for one more on this video before having to go teach. So we'll move on to question 4d, pardon me. Okay, so I can see from this arrow that I already found all the possible rational roots of this expression, but it also kind of looks like I might be able to do it by factoring by grouping. I am not sure. It doesn't look great because these have the same coefficient but These don't, so it doesn't look like they have a lot of symmetry. I'm just going to double check. Can I factor by grouping? I can factor 3x squared out of the first term. I get x minus 1. I can factor negative 3 out of this term, and so I get I've got 5x minus 2. Okay, so factoring by grouping doesn't work. Okay, so in that case, I'm going to probably need to use some of these helpful steps here. I started by finding all my rational roots. So possible roots are just the factors of this one divided by the factors of that one, and I already wrote down those solutions earlier. So possible roots of this expression are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/3, plus or minus 2/3. So that's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/3, and plus or minus 2/3. All right, so we're going to test those guys. I'm going to try d of 1. That's a nice simple one to start with and just see what happens. So I'll get 3, take away 3, minus 15, plus 6. And these guys cancel out, so that's 2 negative, so not equal to 0. Therefore, x take away 1 is not a factor of d of x. Okay. So I'll try d of negative 1, see if that works. And so that'll give me a negative 3. And take away 3. I get plus 15. And then I get plus 6. And I really don't think that's going to work either, because those negative 3's cancel out with the 6 and leaves me with still positive 15. So it's still not equal to 0. So therefore, x plus 1 is not a factor of d of x. All right, well, I guess we'll move on to 2. So d of 2, I'm going to slow this one down. So it's going to be 3 times 2 cubed is 8, minus 3 times 2 squared is 4, minus 15 times 2, which is 30, plus 6. All right, so it's 24, take away 12, take away 30, plus 6. And I can see negative 30 and is going to cancel out with 6 and 24 because those together make 30 as well. So that's again not equal to 0. So therefore we get x minus 2 is not a factor of d of x. Okay, that sucks. Try another one, d of negative 2. So that's going to give me negative 24, take away 12, plus 30, plus 6. Oh, that's looking good. That does equal 0, because those guys together are negative 36 and positive 36. You can check with your calculator if you don't believe me. And I get x plus 2 is a factor. All right, happy days. So that's great. And so what we just did is step 3 there, I guess. And that's step 3. Now step 4 is we're going to use long division to divide our polynomial by our known factor. So we're going to do step 4 here, which is to use long division to divide x plus 2 into 3x cubed minus 3x squared minus 15x plus 6. So I'm going to, we've done a lot of practice with this, so I'm just going to go through that kind of quick. X squared, 3x squared, 3x cubed plus 6x squared. I'm going to subtract them, and that's going to give me negative 9x squared multiply negative 9x. Oh, I forgot to bring down negative 15x. All right, so it's negative 9x squared, take away 18x, subtract those, and it's going to give me 3x plus 6. Last one, plus 3. Oh, I could have factored a 3 out of this and made this a little simpler. Okay. All right, I could have done that. I didn't see that. I can see that 3 is a factor of all these. All right. So let's finish this off. I'm going to take away 3x plus 6. get 0. Okay, so therefore, we have our d of x is really equal to x plus 2 times 3x squared minus 9x plus 3. And I'm going to try to factor that. First, I'm going to use common factor. I'm going to factor this 3 out. 3 is a common factor. So I'm going to bring that out all the way to the front. D of x is 3 times x plus 2. And I'm going to be left with x squared. Take away 3x plus 1. Weird. Okay, it doesn't look like I'm going to get any common factors out of that, so I'm going to use the quadratic formula for that. All right, cool. So it's all factored, and I'm going to start by sketching now. So I'm going to sketch my x-intercepts, and so I'm going to find that my x-intercepts are going to give me that, I get x is -2, so there's a point at -2, 0, and I'm going to have to use a quadratic formula here. So this is going to give me x equals 9 plus or minus, x equals 3 plus or minus the square root of 9 minus 4 times 1 times 1, which is 1, all over 2 times 1, which is 2. All right, so x is 3 plus or minus the square root of 9 take away 4, which is 5 over 2. All right, so that means that x is approximately equal to, what do we have, 3 plus root 5, 3 plus root 5, divided by 2. So we get 2.6 and 3 take away root 5, divided by 2. And x is approximately equal to 0.4. All right, so we end up with, so I'm at 2.6 and 0, and 0.4 and 0. All right, so I'm going to sketch that out. So we got one at -2. I've got one at 2.6. I'm going to call that 3 plus root 5 over 2. And I've got one at around 0.4, which I'm going to call 3 minus root 5 over 2. Okay. My leading, this is a third degree polynomial. So therefore 2 terms. All right. I know my leading coefficient is +3, so therefore it's going to be finishing upward like that, so it's going to move up like so. And lastly, I'll find my y-intercept, which is pretty easy. My d of 0 just gives me 6. So 1, 2, 3, 4, 5, 6. All right, so I can already, there's no multiplicity, so I can just go ahead and sketch. And we get a graph that looks something like that. Okay, I'll finish the rest of this video, or rest of the solution key in the next video. But good luck studying, and let me know if you guys have any questions about this stuff. How do I stop? I feel like my grandparents.